In the past several investigations, we've been examining and using functions. Recall that a function takes an input value and determines exactly one corresponding output value. In this investigation, we will look at reversing this process and seeing if we can determine exactly one input value if we are given an output value. To explore this idea, consider the following scenario. A particle begins moving directly away from a wall at a constant speed of 2 meters per second. This is shown here. Let's let t represent the number of seconds since the particle started moving, and let's let d represent the particle's distance from the wall in feet. Given any value for t, we can determine exactly one value for d by merely doubling the value of t. So therefore, d is actually a function of t. So d is a function of t. And we'll call this function f. And therefore, f of t is equal to d. Since we know exactly how t and d are related and vary together, we can actually write a formula for f. So f of t will actually be equal to 2 times t. And this is because the distance, the particle's distance from the wall in meters, is always 2 times as large as the number of seconds since the particle started moving. Now let's take a slightly different perspective on this scenario. If we know a value for d, can we determine exactly one value for t? For example, if we knew that d was equal to 6, could we determine exactly what the value of t is? In this case, we should notice that t should be equal to 6 divided by 2, which is equal to 3. And this is because the particle moves at 2 meters per second, so if it's 6 meters from the wall, it has to be half of 6 seconds since it started moving. Now, given any value of d, we can actually determine that t will always be equal to half of d. And in this case, t is actually a function of d. So we can actually define a function g, which takes as its input a value of d and outputs t. So t is also a function of d, and we can define a function to represent this relationship. So if we look at our two formulas, our two functions that we have, both of these functions represent the same relationship. So both of these functions are really representing the same relationship between t and d, but in some way they're in reverse. The input and output variables are reversed in these two functions. When this is the case, we say that f and g are inverses. So f and g are inverses. And this is a new term. We might also say that g is the inverse of f. And this is because g represents the same relationship, but the input and output variables are reversed. This is the idea we will be looking at in this investigation, and we will also introduce a new notation to represent this idea. Since g is the inverse of f, we might actually write, so instead of writing the function g, it'll be common to write f inverse of d equals t. So instead of writing this g of d equals t, we might actually write this right here. So we're just renaming the function as f superscript minus 1 instead of g. And this is a little more precise since it tells us that the function we are looking at the inverse of is f.